Welcome to my talk, C++ as a microscope into hardware. So today we'll try to use C++ to figure out how a CPU works. Before we start, a little bit about myself. My name is Linus. I'm a C++ developer. I've been doing it for a couple of years, and I've been pretty much switching back and forth between autonomous driving and finance. Currently, I work for a company called EngineersGate. It's a finance company based in New York. I happen to really like it there. They value their employees. They really care about well-designed and performant software. So if you want to talk to me about EngineersGate or about anything that I'm going to mention in today's talk, just go find me afterwards. Right, so my name is Linus, so I'm required by law to use Linux. So today's talk will focus on Linux on x86-64.
But you're not wearing sandals with socks.
All right, so I know there's a lot of people here who know a lot about the hardware and the CPU architecture, but let's just start by pretending that we don't know anything. It's just like a box that does some magic. The only two things we do know is that it has some memory, because whenever we write a computer, they tell us how much memory it has. And the second thing we know is that it can compute stuff, because it's a computer. So throughout this talk, we want to refine our model of the CPU, and hopefully by the end of the talk, we will have evolved our model to such an extent that it'll be a fairly good representation of what an actual CPU, a modern consumer CPU, actually looks like. And the way we want to get there is we want to ask questions about the CPU, and we will try to answer those questions using C++, some assembly, and some other tools that I'm going to introduce. Whenever we observe a discrepancy between our model and what we observe in the test, we'll refine our model and evolve it, and to finally arrive on the right-hand side. Why do we want to do this? Well, first of all, I think there's two reasons. First of all, it's super interesting. It's crazy what kind of tricks hardware engineers pull to make software run as fast as possible. And then the second reason, I think, if you care about performance, you can't ignore the hardware that your program runs on. You need to have some kind of idea about the theoretical performance limit. And if there's a discrepancy between the theoretical limit and the observed performance, you need to be able to figure out what's going on. You need to know the hardware, and you need to know some tools to debug your program. So my first question that I'm going to ask is, how do we even communicate with a CPU? How do we tell a CPU what operations to run? We're all software engineers, so obviously we write some code. Here's an extremely simple piece of code. The hardware, though, doesn't understand C++, so we first have to compile it into a binary. And let's just look what the binary looks like. It's a bunch of garbage, because the CPU only understands binary data. There is some information, though, we can read. Here's the file format. It's the L file, which is typically used on Linux. There's some information about the build environment, and then if we scroll down a bit, the L file is there's different sections. And today we're mainly interested in the text section, which is where the executable code lives. Yep.
Do you know why it's called text?
No.
I've been searching for an answer to that.
No, I don't know.
Okay.
So I haven't even searched for an answer, but if you don't know, then I won't even try. All right, so this is obviously not how the CPU looks at an object file. The CPU looks at it in binary format. So something like this. This is the same object file, just dumped as a binary. If we wanted to interpret this as software engineers, we would probably write a program that opens this file, tries to interpret all the ones and zeros that are in the file, and then once we have interpreted that, we could call a function that emulates the hardware behavior. So this is what I think most of us would do in software. The hardware pretty much does the same thing, just it's not called open, interpret, run. It's called fetch, decode, execute. So this is the basic pipeline that we'll keep coming back to throughout the talk. I'd like to start with the decode stage, though, because I really want to know what do all these ones and zeros mean, what is encoded there, and we can do that by doing the decode stage in software. So we can disassemble the binary into assembly instructions, and you can pretty much go back and forth between binary and assembly. So let's disassemble this and see what it looks like. So the first tool that we're gonna use, that I'm gonna introduce today, is object dump. We'll use it a bunch of times throughout the talk, and it just like looks at the binary and disassembles it. This is what the output looks like. We can see the name of the object file, again the L file format, and this is the disassembly of the text section, where again the executable code lives. The first column here is just the offset. The second column is the binary data that we saw in the previous slide. And then we see that encoded, there is different instructions. So for example, here there's 2 instructions encoded, move and return. And some instructions take operands. So move takes 2 operands, the destination and the source. And return doesn't take any operand. Now, if we wanted to find out what kind of instructions there are and what kind of instructions are supported by the architecture, we can just do this process for different input files. And that's what we're going to do. So let's start out with the program we just looked at, or the function we just looked at. And right away, we can see we have different instruction lengths. So not all instructions take the same length of encoding. This is different for ARM, where all instructions have a fixed length. On x86, they can be anywhere between 1 byte and 50 bytes, I think. And we can already see that the decode stage has a lot of work to do, because it doesn't only have to decode the instruction, it also has to figure out how long they are. All the instructions are specified, there's a manual by the vendor, and you can open it, it's gigantic, and it'll tell you all the encodings for the available instructions. Then we can see if you want to return a value, here we do it through EAX. So it'd be just a convention that everything is returned through the AX register. Here we return a 32-bit value. If you wanted to return a 64-bit value, we use the same register, but we can specify what section of the register we want to use. So EAX uses the bottom 32 bits, and REX uses the whole register. Now let's compile this with O1, and now we can see that there's different types of registers. For example, the EAX register here is changed by the callee, and then the caller will be able to observe that change. For the base pointer, before we change it here, we save it on the stack. So we push the value on the stack, and then before we return from the function, we pop it off the stack back into the register. So the caller won't know that we even use that register. And so this is called a volatile register. RAX would be a caller-owned register. In this example, we can see if we want to pass a value to a function, we also can use a register for that. There's part of the convention is what order registers are used in for multiple arguments. And the return register, volatile or caller-owned, and which ones are used as function arguments is all specified in the calling convention. Again, this is nothing that the hardware requires. This is just a convention that we have to agree on. If I compile a program and use someone else's library, we better agree on how we pass values, because otherwise it just won't work. There's a different calling convention for Windows, but thankfully, the compiler takes care of this, so we don't really have to know about it. We can have the function body a bit more complicated to see a couple of more instructions that are available. And if we have a ton, if we want to pass a lot of arguments to a function, eventually we'll run out of registers, at which point we'll just use memory. So we can, in the binary, also refer to memory locations directly. Now, we could keep going with this process, but it is kind of tedious and lengthy. But I really want to know what instructions are available and which ones are common ones. So a different approach we could take is just object dump an existing binary and try and get some stats from that. So if we object dump this and just look what kind of registers are being used, how often are they used, we get this graph here for GCC. And kind of makes sense that REX is used the most because it's the return register. So whenever we want to return something from a function, we have to use REX. if we do that, like we could arrive at this overview. This is just, there's 16 general purpose integer registers that we can refer to. There's more for SIMD and for floating points, but like for the purpose of this talk, we'll just focus on those ones. As I mentioned, you can refer to different subsections of a register. These are kind of reserved registers that are off limits for us, used by the CPU. Here's the calling convention. This is the order arguments are passed. All these are volatile registers, so the callee can change them. And then there's a couple of caller-owned registers. We can do the same thing for instructions and dump like how often they're used. You can see move is by far the most common instruction that is used. So like most programs are just about moving data around. And you can see like these top 12 instructions account for 77% of all instructions that are being used. So you don't even need to know that many instructions to kind of be able to read assembly. All of those instructions are pretty self-explanatory, like nothing crazy going on here, XORs, compares, jumps. So like not that difficult. I think like the only two kind of weird ones is move, because it copies, it doesn't move. And then the LEA instructions is very commonly used. It's just a fancy way of adding. So if we compare it, like an add does pretty much a plus equals add, and the LEA does x equals y plus z. And it's also very useful to determine the index in an array. You can do that with one instruction because the second operand also allows to be shifted. So yeah, very useful. That's why it's used so often. All right, so at this point, my question was like, we can write 70% of GCC with these 12 instructions. So do we even need more? Like, would we be able to write the whole of GCC with those 12 instructions? Or are there any other ones we might have to add to be Turing complete? So I Googled it. How many x86 instructions do you need to be Turing complete? Any guesses?
3.
3?
4.
4? Pretty close. It turns out you just need 1.
Oh, no.
So there's this paper called Move is Turing Complete. It starts with the sentence, the x86 instruction set is overcomplicated and redundantly redundant, which is a great way of saying something is redundant. But like it sounds extremely hard to believe and kind of a clickbaity title. Second sentence is it remains Turing complete when reduced to just one instruction, which apparently is the move instruction. Now, in theory, we could open that paper, try to reason through it, understand it, but I think that would be very dry, and we just want to try out stuff here. And luckily, there's a guy on GitHub who also read that paper and was like, I bet I can implement a compiler for this. So now, in order to find out if move is really Turing complete, we just have to get a random program, C program, compile it with the movecc compiler, and run it and compare the output to a GCC version of the same program. So I went to Wikipedia, found a random program. Doesn't really matter what it does and how it does it. It just needs to be some kind of program. And then I went ahead and compiled it with the movecc compiler. And we can object dump this to like verify that it really only does use move instructions. So this is just like moves all the way down. This is truncated, so the total binary was, I don't know, 3,000 or 4,000 moves. Any guesses how long how many lines the object dump of the same program has with GCC? So 3,000 or 4,000 for move only.
100 maybe.
100.
20.
Not bad. It's 50, I think. Oh. Yeah, 52. I ran both programs. They gave the same output. If you still don't believe that move is really Turing complete, on the same GitHub they have a version of Doom with just move instructions. So if you want to play that, go ahead.
How's the performance?
Good question. So if you look at this from a hardware perspective, like if we only have to decode move instructions and if we only have to execute move instructions, arguably, the hardware could be much, much simpler if compared to having to support hundreds of instructions. So there must be some kind of catch there. And To look into that, I'll introduce the next tool that we're going to use. So we have been using object dump. The next tool is going to be Perf. Perf gives us access to hardware counters, and we can observe like many events that occur in the CPU. For a full list of observable events, you can do perf list. Some of them require like sudo access, so you get even more if you do sudo perf list. And then we can use perf to analyze any program. So here's a little example. I'm specifying the hardware counters I'm interested in. I run it for ls, and then perf just gives us the following output. So we can see the total duration, the number of CPU migrations, instructions executed, and so on. So let's run the move-only version of our program and the GCC version of our program with perf and see what we get. And you can see like the move-only version takes 2,500 times slower than the GCC version, and takes as 800 as many instructions to be executed. I didn't play this. This was just it said so on the GitHub page, but every single frame to render for the Doom takes 7 hours. So clearly, like this is interesting, but from a performance perspective, it makes absolutely no sense. And my question then was like, why would anyone go through the trouble and like write a whole compiler that no reasonable person would ever use? Luckily, there's a FAQ on the GitHub with one question and one answer. The question is, why did you make this? And the answer is, I thought it would be funny. I have to agree. All right, let's recap what we've done so far. We looked at the ELF file spec, the instruction encoding, the calling conventions. And at this point, I think we know enough to throw away our fancy mechanical keyboards and just code the binary directly, which is nice. We used two tools, namely object dump and perf. We looked at different instructions and registers, but we haven't really looked at the memory. So we know we can refer to memory, but we don't really know like where different stuff lives in the memory, how it's laid out, how it is laid out. So let's have a look at that. And we can use C++ to kind of get an idea about that. So we create a vector of a string to pointer pair. And now we can put different items into that vector. We can put some like global variables and some functions in there, some stack and heap pointers, some command line arguments, and environment variables. And then we can use ranges to sort it with a projection. So we sort it by the pointer, and then we can just print it out to get an idea about the memory layout. And what we get at the highest memory addresses, we have the environment variables and then the command line arguments. Underneath, we have the stack that grows downward. Then we have the heap that grows upward. And then we have global variables and functions. The address of the global variable here is actually like encoded into the binary. So if we used if we dumped our binary, we would find that address in there somewhere. So my question is like, what if two programs use the same memory address? Like, what will happen? Based on our current model, we would expect that they can interfere with each other. So that's my first question that I have. The second question is that there's a huge address space between the stack and the heap, and I'd be interested to know like what happens in between there. Like, how much stack space do we have? How much heap space? So let's start with the first question. I will run this little program twice in two separate processes at the same time. So we have an atomic int. It's atomic because we will try and access it from two processes. We will increase that global variable, and then we will print both the address and the value. I'm just printing the address here to really show that both processes use the exact same memory address. And based on what we know so far, we expect that each process increments the value at the same memory location. So in total, there will be 2 increments, so the answer should be 42. If we run it, we in fact get the answer is 41, which means that the memory addresses that we see here, they can't be real. Like, it can't be the real physical memory address. Instead, it is a virtual memory address. So the OS maintains a mapping for each process, a different table from virtual to physical memory address, such that different processes can't interfere with each other. We saw earlier how many move instructions are, for example, in VCC. So a lot of those instructions are memory accesses. If we always had to ask the operating system to do the translation between virtual and physical memory, that would just take forever. So instead, CPUs have a cache that caches the translation in the cache that is called translation look-aside buffer to just like speed up the translation between virtual and physical addresses. Okay, so we have answered the first question we had. They have different address spaces, can't interfere. Now let's look at the stack and the heap. For the stack, we can we have the struct with 1 megabyte of size. We can instantiate an object of the struct on the stack. Then we'll create a new stack frame and create another object on of the stack, and we'll print the difference between the first one and the current one, and recursively call this measure stack size function. Eventually, we'll run out of stack space and crash. So this is what happens, and we can see we just have like a couple of megabytes of stack space. We can do a similar thing for the heap. This time we'll do a gigabyte, not a megabyte. Presumably there's a bit more heap space. And then we try to allocate these 1 gigabyte things on the heap over and over again until we run out of space. If we do that, we find that we can allocate 130 terabytes of memory, which doesn't make sense to me because I can guarantee that the machine that I was running this on doesn't have 130 terabytes of RAM. So if you look at this in HTOP, we see that the amount of virtual memory is in fact like very close to what was printed, but the actual memory that was used is like barely anything. So when we ask the OS for memory, it'll happily give us a virtual address, but it won't back it up with a physical address until we really need it. So next question is, what happens if we actually need it? If we actually like access the memory. So here, similar program, instead of like doing it indefinitely, I'm just doing it for 30 gigabytes. The machine I was running on had more than 30 gigabytes of memory. I just didn't want to run out of memory. And then what is the smallest change I need to make here to really access the memory, like in characters?
Sorry, what?
What is the smallest change I need to make to this little snippet to make it really access the memory?
I would guess like if you touch 1 byte per page,
Yeah, so in the smallest way I could think of is just to value initialize everything. So 2-character change. Now let's run this under Perf. And the left-hand side takes very little time, and the right-hand side is almost 20 seconds. Now, the reason could be that it just takes that long to write like serials to all the memory addresses. That could be one explanation. But that, just to be abundantly sure about this, we could just check all the different perf stats that we have access to and compare it between the left and the right-hand side and see if we see any major discrepancies. And if we do that, we do see that the number of page faults is very different between the two versions.
But these are page fault, like minor page faults, just for, it's not that your system ran out of memory.
No, there's minor page faults, yeah.
Okay.
So what a minor page fault is like, we have this virtual memory address, and now we really want to write to it. So the OS is like, oh, I gave them a virtual memory address, but it's not backed up by physical memory. So I need to find a physical memory address and do the mapping, and that is what happens when a page fault occurs.
I just want to add something really important for the C++. So when you write your code, you want to make it everything so bulletproof. You try, you allocate when you catch bad alloc, nothing happens, you write, and then your program crashes. This is the reason why that happens. Okay. So it seems like in the modern programming, C++, malloc will always succeed, essentially.
Yeah, because you have so much virtual memory.
Yeah, and that's why you need to do this initialization for big blocks.
Yeah, so this is a behavior in Linux. They call that overcommit, where they basically always give you memory lazily allocated, but it can actually be disabled. Even within Linux, there's I forget the exact path, but there's configuration thing inside of sysfs that if you change a number there, you remove that behavior, and you can start seeing memory allocation failures in C++ programs. Right?
Okay, all right, cool.
Quick question from the last slide. Is there anything specific about 130 terabytes that's where it failed?
Maybe it runs into the like stack memory address space. Not entirely sure.
So the hardware has a 48-bit address space, which is
But if it's a Linux, if you were running on Linux, it's a configurable thing to sysconfig. I don't know something.
Okay.
Yeah. So there is a limit on
what
how
he said
much.
is that it's a CPU limit.
Maybe in this case, but there is also a operating system limit.
Okay, so let's look a bit more into these page faults. So we don't really know if the increased amount of time is due to just writing to the memory or if it's because of the page faults. So let's look into this. And for this we need to add another thing to our toolbox, the timestamp counter. So the timestamp counter is a hardware counter that just increments by 1 on every clock cycle. So if we have the struct that reads it on construction and reads it again on destruction, we can like calculate how much time was spent in a scope. So this is called profile scope, and that is what we're going to use. I expanded it a little bit, so it doesn't. The version that we're going to use doesn't only keep track of the elapsed clock cycles, but also of the occurred page faults. So here. We allocate 3 gigabytes of memory, we measure how long it takes, and then we will read from those bytes. So we will touch every single byte in this 3 gigabyte range, and I'm just like using the result to make sure that it's not being optimized away or anything. So down here we'll print a result, and we will run the same loop twice. So in theory, like we would expect, maybe it should take on both iterations, it should take the exact same amount of time. But we do know that on the first iteration, we might get page faults because we haven't mapped it into physical address space. So maybe the first run takes a bit longer. So let's run this. And we see, so the first block here is just to do the mmap. That barely takes any time. Is this big enough for everybody?
Make it a bit bigger. Yeah, better.
All right. So the first block is just measuring how long it takes to do the mmap, which barely takes any time. Then the second block here is how long it takes to read the data on the first iteration. And we can see we get a ton of page faults. And the runtime accounts for 90% of the overall runtime. On the second iteration, we don't get any page faults. We still read the exact same amount of memory, but we're much faster.
How did you count how many page faults there were?
It's, what's the function? It's like
a built-in.
Yeah, it's a built-in, yeah. All right, and then, so the second time when we don't have page faults, we are way faster. So we can see there's like a serious performance impact of page faulting so many times. What we also see, we still don't use that much physical memory. So the virtual memory we use is 3 gigabytes as expected, but the physical memory we use is still like barely anything. And the reason for that is when we just read, we don't need to read from like different physical addresses. We just want to read zeros. So the operating system maps all those virtual pages to the same 0 page. And then we'll keep reading from the same physical page over and over again. Another thing we see is the bytes per fault. So we get 4 kilobytes per fault, and that is the page size. So whenever we want to request some memory, it's always in page sizes. So if you just want to request 1 byte, we still get 4 kilobytes. Now what happens when we also write to the memory? Again, the first time we read is much slower than the second time we read, and the first time we write is also much slower than the second time we write, because before we write to it, all those virtual memory addresses point to the same read-only 0 page. When we actually write to it, we have to page fault again, and then the OS really has to find different physical memory locations for us to be able to write to. And we see that now we really use physical memory, like as expected, 2 gigabytes. Okay, yeah, so this was the memory demo. Next, I'd be interested to know how, like, what's the bandwidth that we have access to? Like, how fast can we read and write from memory, and how maybe it depends on the memory size we want to access. So for the first test, we're just gonna do a sequential memory access, and we'll sweep the total range that we are accessing. Second test is we do the same thing, but in random order. And then the third test is we don't sweep the range. We always like iterate over the same amount of memory, but instead we'll change the stride size. So the first run we'll touch every single byte, the second run every other byte, then every third byte, and so on. So let's start with the first test. And to do that, we again expand our toolbox. The read timestamp counter is like very convenient, but if you do micro benchmarks, it can fluctuate quite a bit. There can be a lot of noise in the measurements. So there's benchmarking libraries that run the same tests like over and over again, and averages over all those runs until it determines that like it's stable enough, and then it'll stop the execution and print the results. It's quite easy to set up. You just have to like specify some benchmarking function and then put your test code in this loop here. So let's do that for the memory write. We get some amount of memory, and the total memory range will sweep from 1 kilobyte to a gigabyte, and we'll increase it in powers of 2. Probably make this a bit bigger. And then we'll just measure how long it takes to copy a value into every memory location. When I run this, you'll see a column like with the timings. You can ignore the time column because I didn't normalize that to the total size we're iterating over. But there'll also be a data rate column, and that column is normalized. So we'll look at the data rate column. Before we start, though, let's have a look at the assembly this generates. So this is the same loop. If we compile this, we see that, as expected, we copy this value into our destination. So that's the move instruction. And that is like the only instruction that we are interested in and that we want to measure. On every loop iteration, we also have to deal with the loop itself. So this will kind of also be part of our measurement, but we don't really want to have that in our measurement result because we just want to measure the performance of the move instruction. So in order to get this, we can just unroll the loop a little bit. So we'll just, in every loop iteration, do more moves than just one, and then we measure more of the move and reduce the impact of the loop itself. So this was on 01. If I compile this on 03, we see that now, even though there's just one assignment in the loop, we get 3 assignments over here in the assembly. There's 2 assignments in the actual loop assembly, and then there's another assignment out here. Does anyone know what's going on here? Yeah, so the compiler can also unroll the loop for us. So the compiler unrolled it twice, and then it just has to deal with the edge case when there's an uneven amount of loop iteration. So we can unroll the loop, the compiler can unroll the loop, and we'll later find out that even the hardware can unroll our loops. Okay, so let's unroll this a couple of times. This is 32 times unrolled, and then we can run this. And yeah, as I mentioned earlier, you can pretty much ignore the time column. What's more interesting is here the bytes per second, because that's normalized to the whole range. And we can see it stays stable for a while, then the bandwidth drops, but stays stable for a while. Here there's a bunch of 16 ones, and then it'll go slower again. So let's plot this. So this is the plot. Like, as you can see, it started like with 23 gigabytes a second, and then went down to 16. So this is like the same values as I plotted here. And this is probably a bit unexpected that there's like these steps here. And in order to figure out what's going on there, we can pick 3 locations. So here at 16 kilobyte, 128 kilobyte, and some value over here in the slow range. And again, we can use Perfstat and see if any of the counters deviate between those different regions. At 16 kilobytes, we see there must be a cache. At 16 kilobytes, we don't get that many cache misses. At 128 kilobytes, we get a lot of those L1 cache misses, so we are probably out of the level 1 cache. And then over here, we've fallen out of all caches. So this gives so there's 3 different cache levels. We can use LSCPU to see the cache levels. So 32 kilobytes level 1, 1256 level 2. And this kind of lines up with what we measured here. Like, this is a kind of a coarse measurement, but at least like it definitely lines up. Okay, so this was the sequential write. The next measurement I wanted to do was the random write. And this is the result for the random write. We're like pretty much the same at very small ranges, but then the performance just like drops way down. And the reason for that is that the hardware, when it realizes we sequentially access different memory locations. So we ask for like byte 1, 2, 3, 4. The hardware realizes that we might like request byte 6, 7, 8, 9, 10 afterwards. So it'll already try to get those into the caches so that they're ready waiting for us when we actually do need them. When we iterate randomly through memory, the hardware can't do that, so the performance goes way down. And this is why it's so important. Like, vectors is great. If we just sweep through memory in sequential order, the performance is just way better than when we hop around. Okay, so we've done the sequential write, the random write. Let's talk about the strided axis. I think what we would expect based on our current model is something like this. So when we access every single byte, we are pretty slow, and then we get faster and faster as we skip more bytes because we have to load less data into memory. So I think this is kind of what we would expect. When we measure it, we get a graph like this, and there's 2 unexpected things happening there. The first one is we don't get any faster in this range here, so we kind of want to know what's going on here. And then the second weird thing is these spikes at 128 and 256 stride size. So let's answer both questions one by one. Let's start with the first one. Why are we not getting any faster here? And the drop is right at 64 bytes, but let's just pretend this was at 3 bytes. So just for the sake of argument, pretend this is at 3 bytes. And then I marked like every set of 3 bytes with this little vertical line here. So if we access every single byte, we are somewhere up here. If we access every other byte, we are somewhere up here, but like haven't gotten any faster. If we access every third byte, we are right at this drop, but still haven't gotten any faster. And then finally, if the stride is 4 bytes, we're finally getting into this region here where we get faster. And then if we skip more bytes, we get even faster. So the reason for this is like we only get faster once we start skipping whole sets of these 3 bytes here. The reason for that is there's cache lines. So in this example here, a cache line would be 3 bytes. And whenever we access 1 byte from a cache line, we have to pull in the entire cache line into cache. So even though we effectively use only a third of the bytes here, we still pull in the same amount of data into the cache as in the example up here. And then only when we start skipping entire cache lines, we actually get faster. And in reality, the cache line size isn't 3, but it's 64 bytes. All right, so this like explains the first phenomenon that we see here. Let's talk about these spikes. I think someone mentioned earlier for memory lookup, we only use 48 bytes. But one job of the CPU is it has to figure out if like a memory address that we request is in cache or is it not in cache. And it has to be able to do so like extremely quickly and deterministically in a couple of cycles. So it ignores the top 16 bytes, and it can ignore the bottom 6 bytes because we know that's like within the cache line. And if we know the cache line is in cache, then every byte in that cache line will be in cache as well. But like there's still a cache can hold a ton of cache lines. So in theory, like we'd have to compare these memory addresses with every single cache line that is currently in cache, which is very expensive. So instead, the cache is divided into different sets. And the first couple of bits, like the lowest couple of bits here, are used to index into a specific cache set. So if we assume this is our level 1 cache, every single entry has a 64-byte cache line. And then we have a certain number of cache sets. So the total cache size is the cache line size times the number of ways times the number of cache sets. And then because we can index into a certain cache set, we only have to check like the couple of ways that exist in this cache set to determine whether this address is in cache or not. Now, if the stride size is 128, then the bottom 7 bytes of this memory address always stay the same. So these bytes for a stride of 128 will always stay the same, which means we only use half of the available cache sets. We'll skip every other available cache set, which means we basically cut the available cache in half. And this is why we see that spike, because we only use half of the total physical available cache for the stride size. For 256, the bottom 8 bytes will be the same. So in this example, we would quarter our available cache, and this is why we see the second spike there.
Wouldn't the spike be bigger then?
Well, we do read relatively maybe, but like we maybe read so little data that we still fit into a low level cache. I haven't really looked into it, but yeah, this is what I measured. I can only assume that like we read so little that we might fit into a low level cache, so the impact is not as quite as high. Okay, any questions? Okay. Let's go on. Okay, recap memory. So we've talked about the memory layout, about heap and stack. We talked about virtual memory, about paging, the TLB, caching, different cache levels, L1, L2, L3. Talked about cache lines, prefetching. Oh, and I forgot to mention the number of ways you have is called the associativity of a cache. So if someone tells you they have a like 8-way set cache associativity, that's just a fancy way of saying how many rows are in this table. Okay, so we talked about prefetching, cache associativity, and some of the tools we used are HTOP, the timestamp counter, and Google Benchmark. The last part of the talk will focus on, so we've talked about like the binary itself, we've talked about the memory. The thing that's missing is like the part of the CPU that actually executes our code. So we'll talk about that last. And in order to do that, we'll add another tool to our toolbox, namely NASM, which is an assembler. So NASM allows us to go from assembly to binary. We previously used object dump to go from the binary to assembly, and we can use NASM to go in the other direction. The good thing about using NASM is that we have very tight control of what will be executed on the CPU. If we use C++, we have to go through the compiler. Compilers are extremely smart in figuring out what we actually want to do. And they often optimize away a lot of code, and then it gets very hard to get the CPU to do a very specific thing. And this is much easier if you control the assembly directly. What we have to do to use NASM is we have to tell CMake about it. Doesn't require that much CMake. Then we have to write the assembly program itself. So we have to put it in the text section. We've learned about that earlier. And then we can write the assembly. We know the move and the add instruction. And we know the calling convention and everything. So we know the first argument that we will pass to this function will be in RDI. The second argument will be in RSI. Adding this like a plus equals add, and then we add into RAX, because that is the return register. From C++, we can declare this as extra C just to get the name mangling right. And then we can just call it from C++. So if we do add 10, 20, we will print result is 30. Okay, so let's talk about the CPU where it executes stuff. We've talked about the fetch, decode, execute pipeline a couple of times. Commonly, fetch and decode are referred to as the front end of a CPU, and then the execute stage is referred to as the back end of the CPU. And I'll use those terms going forward. So keep that in mind. The front end is the fetch and the decode, and the back end is the execute stage. I have a couple of assembly snippets here. They come in pairs here. So this is the first pair, second pair, third pair. The difference between the pairs is that the first versions, they just repeat this assembly line 100,000 times. So this percent rep is not an assembly thing, that's a NASM thing. And what it does is it's just like takes whatever is between the rep and the end rep and just copy pastes it a certain number of times. Here we do the same operation in a loop. So instead of having this add RAX9 line 100,000 times in the binary, we just have it once, but then we keep looping over it for as many times as we pass into the function through RDI. So if we pass in 100,000, then this will loop 100,000 times. So for the first pair, we just add a number into RAX. For the second pair, we do a no-op. A no-op still has to be fetched and decoded by the front end. It'll be issued to the back end, but the back end will just drop it on the floor and not do anything. So the second pair here just does a no-op, and then the third pair also does a no-op, but it uses a different encoding of the no-op. So in the beginning, we talked about that like the vendors specify the encodings of every single instruction. No-op has different encodings, so you can encode a no-op with just 1 byte or with multiple bytes. So here I'm just using a no-op that uses 9 bytes instead of 1 byte. So the program will execute, still won't execute anything, but the binary will be bigger. Okay, so let's again do a little demo. And let's just start with the add. All right, so this is the first code example I had on the slide, which just does 100,000 adds. So again, this rep and rep would be the same as if I had this add line 100,000 times. Let's see how long this runs. And this takes 32 microseconds to run. Now, we know 100,000 adds were done in this 32 nanoseconds. So we can calculate how many cycles does it take per add instruction. We can, and in order to do that, we just need to know the time, the number of adds that were done, and the frequency of the CPU. And if we look up the frequency of the CPU with LSCPU, it's 2.6 gigahertz. Now, if we use 2.6 gigahertz, we would calculate that an add instruction takes less than a cycle, which doesn't make any sense. So the CPU can run at different power states. It can run at lower frequencies to save power, and it can increase the frequency in order, if it's performance critical. So LSCPU just gives the default frequency. To get the actual current frequency, we can use CPU power. And we see that the CPU currently actually runs at 3.1 gigahertz. So now we know all the values to actually calculate the cycles per ad. I just need to go back here to the timing. So let's just copy this and paste that in here. And then if we execute it, we get the cycles per, like one ad takes one cycle. Okay, and then if we run it in the loop, now instead of just having 100,000 instructions that we are going to execute, now in addition we have this decrement and this jump not zero. So now we will, instead of 100,000 instructions, we will in total execute 300,000 instructions. So we don't really know what's going to happen, but like one sensible thing to assume would be that it takes maybe 3 times as much, but let's just run it and find out. So we see, despite executing 3 times as many instructions, it still takes pretty much the exact same amount of time. And that tells us that the front end, so the fetch and decode stage, can decode multiple instructions per clock cycles in parallel. So it needs to fetch enough data to be able to decode multiple instructions in one clock cycle. And it also has to decode them in parallel, and it also has to figure out where the next instructions start, because like we have a variable instruction length. So if it needs to know, if it wants to decode multiple instructions in one cycle, it kind of has to guess where the second instruction starts. Yeah, and apparently it can do that all in one cycle. So if we want to know how many instructions in theory we can decode in one cycle, we have to make sure that we're not bound by the backend. So the next example, the instructions will be a no-op, so we know the backend won't have to do anything. This will be entirely front-end bound. So let's execute this. And we can see the no-op, it's still 100,000 no-ops, but the total execution time is 1/4 of the ad version. So we know at maximum we can decode 4 instructions every cycle. Now let's do the same no-op in a loop. Yep.
When you do the rep,
Yep.
so you ran 100,000 NOPs, but you only ran it once, or the test ran it several times?
So the test, the Google benchmark test ran 8,000 times. That's the number of iterations here.
Okay.
But the timings we see is like the total time divided by 8,000. So this is like per iteration.
Right.
Did that answer your question?
Yeah.
Okay.
Because otherwise it would make sense. Right?
Yeah. All right. So we know we can decode for instructions per cycle if you're not bound by the back end. So let's run the loop version of this no-op. And we're back at the 32 microseconds. And the reason for that is this decrement RDI. This is pretty much the same thing as add the EAX that we do here. It's just a giant dependency chain, because you can't do the decrement of the following iteration until you have done the decrement of the previous iteration, because you need to know the value of the previous iteration in order to be able to do the decrement. Okay, let's switch back to the slides and just like see some stats about this. We've done the add, so this is more perf performance counters. We can see the number of instructions that were actually executed, and the job of the front end is to always have many instructions waiting for the back end to execute. So the back end has always like enough work to do to do as many instructions in parallel as possible. So the front end tries to like race ahead of the back end and decode as much as possible, and just like shove the instructions to the back end, and then the back end can pick and choose what instructions it can run at a time. And that is why we have this queue here between the front end and the back end. So the front end just like puts as many as possible operations into this queue. If you look at this add instruction here, takes 32 microseconds. We issue, like we want to execute 100,000 instructions. This is in thousands here. We issue 100,000 instructions to the backend, and then the backend actually executes 100,000 instructions. If we do it for the loop, we see the first weird behavior. So as expected, the number of instructions we want to execute is 300,000, but then the front end only issues 200,000 instructions to the backend. And the reason for that is that the instructions that it issues to the backend are different from the instructions we see in the assembly. The reason for that is that we have some assembly instructions like add EX, 1, and the backend has to do the exact same thing as when we just increment EX. So there's multiple instructions that we can have in the assembly that decode to the exact same instruction or operation the backend has to do. So the front end just does a mapping from all the instructions that are available in the instruction set to all the instructions that can actually be executed on the backend. And the number of instructions that actually have hardware support on the backend is smaller than the number of instructions that we have access to in assembly. So this is a more reduced instruction set, these micro operations. So the instructions that the backend executes are called micro operations, and we don't really know what they are because the vendors don't really tell us, but yeah, they exist. Yep.
Yeah, doesn't this lower number induce that there is a special instruction in the microcode for increasing by 1?
Yeah, so some instructions, like the add instruction, the mapping is 1-to-1. So for one add instruction, there's one micro-op. Some instructions, like one assembly instructions, maps to multiple micro-ops.
Okay.
So it can be 1-to-many. And then some instructions, like this decrement jump, they're so common that they actually map to one micro-op, and the process is called micro-op fusion. So some assembly instructions can be fused into one micro-op.
To be fair, the front end also has a loop opcode.
Has a what? Oh, micro-op cache. We'll get to that. Do you mean?
No. It's something from the 8086 days, where there's a loop opcode that does both in a single opcode.
Okay.
It's not used today because it's just for legacy. But
okay, so you're saying there's a loop assembly instruction that basically fuses those two into one.
Yeah, but I think it uses RCX or so. Okay,
yeah, there's many instructions on x86, which is why the paper earlier said it's overcomplicated and redundant. Okay, so for the no-op, we get faster, we issue 100,000, and we want to execute 100,000 instructions. We issue 100,000 instructions, but then the back end drops all of them on the floor. So this is pretty much expected. Nothing interesting going on in the no-op loop. Now, the 9-byte no-op, the back end still doesn't do anything. We still issue the same number of instructions as in this no-op here, but we are significantly slower. Now, what's the reason for that? We can again look through all the performance counters, see if we see anything interesting, and we see these iCache misses. So we saw the data caches earlier when we did the bandwidth measurements. So we know there's a data cache. There's also an instruction cache. Instructions and the instruction stream and the data stream use the same level 3 and level 2 cache, but the level 1 cache is different between the two of them. And the reason for that is just for latency reasons. So you want to have the lowest level cache as close to where the values are needed as possible, just for the electrons to not have to travel too far. So the level 1 instruction cache is physically situated right next to the front end, and the the L1 data cache is physically very close to the back end.
That's not the whole. On Intel, that's not the whole story.
Okay, so
Intel, the CPU, a modern 64-bit x86, when you power it on, is in real 86 mode.
Okay.
So it essentially emulates a CPU that was came to market in late 1970s. Since then, CPU architecture changed considerably.
Yep.
So there is a very strong disconnect between the opcodes that the CPU can do and the architecture that does them. What Intel does is it decodes, the first time it goes over the machine language, it decodes the instructions into the instruction cache. So it actually translates the legacy CPU, the legacy opcodes it gives you into the more modern opcodes it executes internally. So on RISC and on ARM, on those, that's the reason there's a separate instruction cache. On Intel, there's another reason.
Okay. So it's not only for latency, there's apparently
and
more.
It also calculates which instructions can be scheduled together.
Okay. Right. Interesting. Okay, but these iCache misses are the reason why we're so much slower. And there's two caches at play here. So there's the iCache that just caches recently used instructions. And there's also a micro-op cache that caches recent decoding results. So if we see an instruction pointer that we have decoded previously, we don't have to go through the effort of decoding it again. We can just look up the instruction pointer in the micro-op cache and look up the resulting micro-ops directly. So two caches at play here. And then if we loop over the same instruction, instead of just having different instruction one after another, we can take full advantage of both the instruction cache and the micro-op cache, and we are faster again. Yep.
I assume 55 is a typo on add iCache misses. Otherwise, that would be way slower, I would think.
I don't think it's a typo, because here we do have a big binary, because we have 100,000 adds one after another, and this add instruction takes more bytes to encode than this no-op. So it stands to reason that we get more iCache misses here than here.
Wait.
Right, but
compared to the
this add to encode takes less bytes than this 9-byte no-op. So the binary size of this will be much smaller than the binary size of this.
I think that it doesn't show up in the perf numbers because that case is back and down. So the iCache only matters when you're front and down.
Gotcha. Thanks.
Oh yeah, right. Yeah. Okay. Any more questions regarding this? Okay. So I've been telling you that the front end tries to race ahead of the back end and decode as much as possible to keep to keep this queue always full so that the back end can execute stuff. This ignores the fact though that we have this jump here. So until the back end has executed this jump, we don't really know if we take the branch or if we don't take the branch. So how does the front end know what to decode next? And in order to find, it doesn't know whether it should decode the instruction after this return or if it should decode this add instruction again until the backend has actually executed it. And to find out what's going on, we'll use another tool called LLVM MCA, which is like an LLVM tool. It stands for Machine Code Analyzer. And what it does, it simulates cycle by cycle a CPU and what it executes. So we can run this. We can specify the architecture. So the machine I'm running this on is a Haswell chip. This is just like an output argument to get a certain output that I wanted to show you. And then we specify the assembly file. So if we run this, we get some output. And this is, so this will simulate those 4 instructions. So add, integer multiply, decrement, and then the jump. If you scroll up a little bit, so what this simulates is every column here is 1 cycle. Oops. So every column here is 1 cycle. Every row is 1 instruction. And each block here, each block of 4, because we have 4 instructions in our loop, corresponds to 1 loop iteration. Now we can see the D stands for dispatch. So even though those instructions, to us, seem they should be executed one after another, they're dispatched all in the first cycle. Then the add instruction here on the first line starts executing right away. We measured earlier that an add instruction needs one cycle, so it finishes executing and then it retires. And retiring means it's committed to memory and observable by the program. The multiplying instruction is dispatched on the first cycle, but then it has to wait for the result of the add instruction because it squares RCX, and RCX holds the result of the add instruction. So it has to wait one cycle, and then it starts executing. Multiplication takes 3 cycles to execute. Then it'll be ready, and it'll retire once it's ready. The decrement instruction.
4 cycles.
I think it's just like the small e's are the representation of when it actually executes. So the add just takes 1 cycle. But like this is not 100% accurate. So like take it with a grain of salt. But like it's kind of accurate most of the time. But for example, like memory fetches, it can't like know how many cycles it will take, so it'll just assume something. Okay, so we've done the multiply, and then the decrement, it doesn't have any data dependencies on like the move or the add, so it can execute it right away. It's done executing before, like in the same cycle, the multiplication starts, but it can't retire it until the previous instruction has finished. And then the jump equal has to wait for the result of the decrement. Once that result is ready, it'll execute and then retire when the previous instructions have retired. So this was all the first iteration. But we see before like we're even done executing the add of the first iteration, we already dispatching the second iteration of the loop. So the decrement of the second iteration of the loop here finishes even right when the add of the first iteration of the loop is finishing, and before the multiplication of the first iteration of the loop is even done. So it'll execute multiple iterations of the loop at the same time, but it won't retire them. Like it'll execute them at the same time, but then it'll only retire them at in the correct ordering. So that's how the front end can race ahead of the back end. It just picks a branch, like it just tries to guess which branch will be taken. It then decodes that branch, it issues it to the back end will start executing it. Hopefully, like it guessed right. In case it guessed right, all fine, we can retire them at the correct time. If it guessed wrong, we won't retire them. So we'll have done some work that was unnecessary. We'll have to flush the pipeline, get rid of everything, and we'll have like done some work that we shouldn't have done, but it will never be observable to the program because it will never be retired. And this works really well for loops, because for loops, like it's very easy to guess. You'll always jump back, except for the last loop iteration. So very easy to predict, and like it gives a great performance improvement. For if-else branches, it can be a bit harder. Like some of them can be very easy to predict, but some of them can be very hard to predict. Based on what we currently understand, we would assume that an easy to predict branch can execute much faster because we'll have to throw away less work compared to a branch that is very hard to predict. So let's have a look at that. Here we have 2 benchmarks. Both of them will do the exact same thing. So we have some vector R with different entries, and depending on the entries, we'll either do a multiplication or an addition. This vector is generated, we do 100,000 iterations, and this vector is generated like so. So half of the first half of the values are ones, and then the second half of the values are zeros. So the branch predictor on the first half will always predict that the branch is true, and it'll figure that out, and then predict all of them correctly until we finally switch to the second half where everything is 0. It'll mispredict it like once or twice, but then it'll figure out the next branch is probably 0 again, and from then on it'll predict it'll predict everything correctly again. So this is the first version that we are benchmarking. The second version is we also we create the same vector with half ones and half zeros, but before we do the loop, we just shuffle them around randomly. Not sure why there's 2 shuffles here. I can get rid of this. So we shuffle them around randomly. So this time the ones and zeros are just in a random order, and it'll be very difficult for the branch predictor to predict which one will be faster. Based on what we understand so far, we would expect the first version to be way faster than the second version. Correct?
Yeah.
Okay. When we run it, we see it is in fact true, so our model holds. First version is way faster than the second version, and we can use those numbers to estimate the cost of a mispredicted branch, because it'll have to flush the entire pipeline. So if we calculate how many in cycles how much the performance cost is that we pay, we can kind of figure out the length of the pipeline that we need to flush. So let's do that. Here I have already filled in the timings. They don't change that much. This is 68,000, and this is 68,000. So I'm not cheating here. But if we execute this, we see that with the predicted branch, the average cycles we need per loop iteration is 2 cycles. With the random branches, it is 12 cycles. So the cost of a mispredicted branch is around 10 cycles. However, because it's random, 50% of the time we probably predicted correctly. So we probably have to multiply this by 2. So the pipeline length will be somewhere around 20 cycles. And this obviously heavily depends on the CPU architecture you're running on. All these benchmark codes, I will give you a GitHub link at the beginning, so you can play around with this if you feel to do so. All right, so this were the branch predictions. Any questions regarding the branch predictor? Okay, the branch predictor, it's very capable. It can figure out strides if you take the branch every other time. Yeah.
Are you going to talk about indirect jumps?
Sorry?
Are you going to talk about indirect jumps within the context of branch prediction?
No, not going to. But what's your question?
Well, no.
I don't have anything prepared for that. No.
The discussions about, for example, devirtualization and invocation of switch statements and so on had to do with the branch prediction in the presence of an address that is data. And I was wondering if. Thank you.
Yeah. No. Unfortunately, I don't have anything prepared on that. Okay, so this is branch prediction. We've seen so far, we've talked about memory addresses. We found out they aren't real because they're all virtual. We talked about instructions. We found out they aren't real because they get turned into micro-ops. The last thing we haven't really talked about is registers. So far, we still think registers are real, so let's look into that. We have here 2 little assembly snippets. Here we have the same add loop that we've done many times now. The reason why I choose 4,000 repetitions is I wanted to be sure that it fits into the level 1 instruction cache. If we use object dump, we can see how many bytes are required to encode these 2 instructions. It's 7 bytes. And given the size of the level 1 instruction cache and the number of bytes, we can calculate how many iterations or how many of those instructions fit into the level 1 cache, and that's why I picked 4,000. All right, so we have two examples here. The first one just does an add into our RCX. The second one does a move into RCX and then an add into RCX. So based on our current understanding, we know this probably takes 4,000 cycles to execute because an add takes 1 cycle. Here we have a dependency on RCX. So we assume that the move will be done in 1 cycle into our RCX, and then the add will be done on the next cycle. So something reasonable to expect would probably be that the second version takes twice as long as the first version. Sound reasonable?
There is an objection, yeah.
Right, so your model might be a bit ahead of what our current.
No, it doesn't have to do with registers. The move doesn't have any dependency on the add.
Right. All right, we'll get to that, but your intuition is completely right. So let's try and figure out what's going on there. So this is the timing. The second version, even though we do twice as many instructions, takes half a month of the time. So what is going on here? All right, so these are the two code snippets. And this one we've discussed before. It's a chain dependency chain. So each instruction depends on the result of the previous instruction. For this one, we need to understand that the processor has something called a RAT. Sometimes it's referred to as the register allocation table, sometimes the register association table. It doesn't really matter what it means. It's called a RAT. And then it has a register file, which has many, many entries. So we have 16 entries here we can refer to, and the register file has hundreds of entries, like, I don't know, 200 or 300. And whenever we write, we redirect the pointer to a register to a different slot in the register file. So let's just assume REX points at slot 42. We moved 1 into REX. So slot 42 in the register file holds 1. And currently, for some reason, RCX points at slot 50. Maybe the value is there, maybe it's not there yet. Doesn't really matter. But RCX currently points at slot 50. Now, if we move something into RCX, we update the mapping. So whenever we write, we update the mapping. So after this move instruction, RCX will point to slot 51. So this the destination is slot 51, and we move from REX. We know REX points at slot 42, so we use slot 42 as a source. Then we add. We look up the source. We want to add into RCX, so we read from RCX and add into RCX. So the source is currently slot 51. We write to it, so we update this mapping here to slot 52 and write into slot 52 the result. And then we keep doing that. Whenever we write, we update the slot. Whenever we read, we look up the current slot, and so forth. Now, for the dependencies, for this add, it depends on S55. So we look up S55, what does it depend on S42, but we know the value of S42. So there's no dependency, like this one is ready to execute right away. So there's no dependency for these two instructions on anything before that. Same, there's no dependency of these two to anything before that. So all like these two pairs and these two pairs can be executed in parallel, and this can be executed in parallel. So the backend has way more freedom to execute stuff in parallel, which is why the second version is much faster. Okay, and then the backend has different execution ports. We saw earlier we can do 4 adds in one cycle, which means there's 4 ports that support an integer add. And then the scheduler just looks at this table, checks whichever one is ready to go, like what dependencies have been satisfied, and then it just pushes those instructions into the different ports to be executed. At this point, we've covered everything that I wanted to cover. This is a block diagram of the Haswell chip where I ran everything on, and we've pretty much covered all of this, which is cool. So now if you look at the block diagram, you should be able to know what the different blocks do.
Will the register association table ever identify registers instead of moving or copying?
What do you mean with identify registers?
So the move RCX, RAX could simply point RCX to the same slot as RX.
Yeah, so there's an optimization here. So register to register move is like the cheapest thing you can potentially do next to a no-op, because all it has to do is to redirect this error here. So that is an optimization.
There may be registers that point to the same slot.
Potentially, yeah, I think so. Yeah. All right. So we've talked about all this. We can even like verify some of our measurements by if we. I can't zoom in, but if we zoomed in here, we would see that there's 4 integer ALUs, so that matches with what we measured. You can see here we can decode an issue for micro-ops, so also lines up with our measurement. So why is all this useful? So recently at work we had like a use case where we wanted to maintain a sorted vector. It should support insert, remove, and update an element. We didn't want to use a set because we wanted to query the top n elements with O of 1 lookup. So we decided to use a vector, and like the simplest implementation that someone could think of is just we put the new, if you want to insert something, we push the new value back and then we sort the entire thing. If you do that in a unit test, it'll function. If you do it on a small amount of number, it might be fast. So it's always good to test these things with a large input number to like get an idea about performance. And we see if we insert, if you have a vector of 1 million 8-byte integers and we insert 1,000 times, the runtime is 46 seconds. But now, like, is this good? Is that bad? Like, we kind of have to understand the hardware to make a statement about this. So let's look at what the hardware at a minimum has to do. Yeah.
Probably not a good example because the big old complexity here is worse than a better algorithm.
Yeah.
So it's not a hardware issue, it's an algorithmic issue.
Yeah, but in order to figure out this algorithmic issue, we have to understand, like, at a minimum, what is the hardware capable of. So let's look at that now. So at a minimum, what we have to do is to find the location where we want to insert that new element. And we can do that with a binary search. So that would be a better algorithm to use. And once we have this location, we can just insert it here, which means we just have to shift back all the succeeding elements. So we can just do this. In algorithms, this would be a lower bound plus an insert. And now let's like reason about how fast should the hardware be able to execute this. Earlier, we measured the memory bandwidth. We know we have 1 million elements of 8 bytes, so we should be at 8 megabytes here. So the bandwidth that is supported by the hardware is like 16 gigabytes per second. We can, like on average, we probably have to shift half the number of elements. We have 16 gigabytes, and then if we do the calculation, we expect an insert should take around 230 milliseconds. So we see like we're way off. We're doing terrible here. So let's compare it to the lower bound plus insert, and we get to 204 milliseconds. We are a bit faster than expected because sometimes we probably get lucky and hit like the level 1 or level 2 cache. But like after doing the calculation, we know like we're like in the right order of magnitude here. Remove, similar, we can do lower bound and erase, similar runtime. For an update, we can just remove and insert, and it takes like twice the amount of time. But again, like it helps if we really think like what changes do we want to do in memory, and not just like concat, remove and insert.
You can do updates faster.
Yeah, so if we think about the memory and what we're doing with remove and insert, we remove the green one, and then maybe we want to insert an orange one. When we remove green, like we want to update green to be orange. And when we first remove the green, we shift these 5 elements left, and then when we insert orange, we shift the 3 red elements back into their original place. So we're doing extra work here. So we could just do this, leave the red elements where they are, and then just exchange the yellow ones with the orange ones. And you already saw this. What's the algorithm?
Rotate.
Yeah. So rotate. So we just have to do 2 lower bounds plus a rotate. And if we do that, we end up with an execution time of 141 milliseconds. This doesn't, yeah?
you said you're putting this in a vector, not a set, because you want an O1 of top n.
Yep.
N is a no number, or is it different every time?
It could be different, yeah. All right, so this was a C++ example. Like I would argue, not only in C++ do we have to like keep memory and time consumption in our minds. Here's a little Python example. Like just imagine like you're tasked with summing all the quantities. So when you develop your little piece of code, you iterate over all things. You get the quantities out. You do a list comprehension. For the debugging purposes, you like print the quantities just to make sure that it makes sense, and then you're supposed to sum all the quantities, so you sum over them. Done. You test it on a couple of elements. Memory consumption is 9 megabytes, which is probably just like the interpreter, because like this shouldn't take that much, but like this also includes the interpreter. But then in production, you have like lots of elements, and all of a sudden your memory consumption is 400 megabytes. Now, like if you know the hardware and like you know the addition can just be like within one register, it doesn't really make sense to need that much memory to do this summation. So like all you have to do is, instead of a list comprehension, do a generated expression, and your memory switch is back down. So like it always helps to test it on a large amount of input and just like kind of reason about is this expected behavior, and if it's not, either improve it or understand why your expectation was wrong. All right, with that, we're at the end of our journey. We've made it all the way from the left to the right. If you want to play around with this, there is a GitHub repository that contains all the code I was using for the benchmarks today. Down below, there's like an overview of all the tools I used. This repository uses the Beman exemplar, which is really helpful to set up all the CMake stuff. And that's it. Thank you for your attention.
So obviously all this means that for algorithm development, we're in a world of hurt, if I'm not mistaken here, right? Because depending on what processor you're using, all of the variables that you've explored here are different, right?
Yeah.
And so, you know, whatever algorithm it is you design, it might perform super well on this set of processors and lousy over here, right?
Yeah, I would say like there's definitely like if you really want to dial it down for one certain processor, like there's another like playing around, like if you have, for example, 5 ads per cycle that you can do, like you can go back from that, and like in theory I could do that many, and then you could look at the algorithm and like max out everything. I agree with you that like that is not a viable approach because there's just so many processor and new ones are coming out all the time. But I do think like there's probably like a nice like trade-off that is reasonably performant for all different kinds
Well,
of.
but then, you know, the other part is you didn't even explore the SIMD avenue,
Yeah.
which means, you know, yet another dimension
Yeah.
here of,
Yeah.
of complication. So, like, even before you're talking about, yeah, it's about algorithm to, you know, just do the sort or whatever. But, you know, how do you compare two algorithms if, you know, this one can run parallel and this one somehow can't?
Yeah.
Right?
Yeah, I definitely agree with you. And then like there's also like graphic cards and everything, so it's hard like to optimize it for all kinds of hardwares that it could potentially run on.
I don't disagree. I don't agree with you completely. Like most hardware is what you described here. This is 95% of the modern CPUs for desktops and servers.
For example, like for SIMD, some CPUs have like 512 wide registers and some don't. And
but yeah,
like
but there are no CPUs without L1 caches. There are no CPUs without branch predictors.
Yeah.
And a lower complexity algorithm over a large number of elements will always run better. So even if we take it into a completely different CPU, so it's very useful to know those parameters, but for most programming tasks, the optimization is on higher levels and unrelated.
Yeah, I mean, like you shouldn't start optimizing the assembly if you're at a suboptimal algorithm. Yes.
So there was much earlier, so I may be forgetting all the details, but you mentioned like some of the performance impacts you had from page cache misses, right? So what thing did you explore using huge pages?
That would obviously help.
Yeah.
Like if you don't have to page fault every 4 kilobytes, but only every like gigabyte or something, that definitely helps. So if you know about the page faults and you know that is the bottleneck, then you could do something about it. So like the important thing is to like have tools to look into it and to understand like how it works. Any other questions? Yeah.
So you had this tool, you were using it on the left side, there was source code, on the right side assembly. What was that tool?
And that is like my own Vim plugin, but it uses Compiler Explorer behind the scenes.
Really? What's the name of the extension?
It's just like on my personal GitHub.
Is it available here?
I think it might be public, so on the GitHub you can probably see it. Yes?
Very important question. You're using Linux with a Windows logo on the...
Yeah, so I logged into, so like, yeah, I'm not very good at Windows, so I couldn't do anything of like that on Windows. I have WSL installed, but like nothing of this works in WSL. So I SSH'd into some Linux box to run everything. All right, and I think we're out of time. Thank you for your attention.